Today I'm going to tell you about the implicit function theorem and astonishing theorem. So you may be wondering right now, why should I care about this theorem? Well, in order to answer this, I need to talk about surfaces. In mathematics, we have basically three main types of surfaces. An explicit surfaces, or simply a function of x and y, an implicit surface, what we're going to be talking about right now, and a parametric surface. These are three types or three different ways to describe surfaces with equations. So, why are implicit surfaces so useful or so interesting? Well, they have very interesting properties. For example, one of the usefulness of implicit surfaces is constructive geometry. Constructive geometry is the following. We can use simple shapes like a cube or sphere or cylinders and then perform building operators like union or intersection and then combine them, right? Like for example subtracting the sets. And even though this seems very simple, we can do very complex shapes with this. For example, mechanical pieces for a machine like a robot or a piece of a car. So this is a very powerful tool for engineering. What else can implicit surfaces do for us? Well, they can also be useful to draw equipotential surfaces. Equipotential surfaces are simply surfaces that has a single value or a uniform value of a certain potential. And for example, right here we have molecules, and this surface around the molecule is a potential surfaces that is colored according to the different value or characteristics of the properties of the molecule. And this is very useful and important to analyze the properties of the molecule, like the charge, the polarity, or hydrophobicity. And this is also useful for drug design, for example. What else can implicit surfaces do for us? Well, they can also serve us to make 3D animations. So let's say for example we want to animate the transformation from a baby to a weird humanoid dragon, and so we can use implicit surfaces to do this. With implicit surfaces is very simple. We simply make a linear combination between the key and the initial state and the final state, or we can also take intermediate states depending on what we want to achieve. And moreover, if we mix this with the previous one, we can also perform molecular simulations, like this one, the fusion of two molecules. So we've seen so far that implicit surfaces are very powerful for different areas. But if they're so powerful, the question is, how often do you use them? And the answer is that we don't use them very often. And why then? Well, the reason is because even though they have many advantages, like this one, the Boolean operators, that we can draw equipotential surfaces and we can easily animate with implicit surfaces, the problem with them is that sometimes they're very hard to draw by a computer. Computers don't manage very well implicit surfaces, and that's the problem. We can do many things with implicit surfaces, but we first have to draw them, and if we can draw them, then we can do the other stuff, right? And to prove that it's difficult for a computer to draw implicit surfaces, I'm going to open GeoGebra, that is a graphical calculator. So here I have a GeoGebra, and if I plot the equation x squared plus y squared plus z squared equal 1, this will draw me a sphere or a ball, right? And this is an implicit surfaces, right? Because we have an equation of x, y, and z. This is basically the form that our implicit surfaces have. But what happens if I try to draw this other one? X squared plus y squared plus z squared plus sine of 4x plus sine of 4y plus sine of 4z equal to 1. What I do again? Nothing. And no matter if I zoom in or zoom out, there is no surface. So we may think, oh well, then it may be the case that this equation doesn't solve or doesn't have any solutions. But indeed it does have many solutions. It has infinitely solutions, so this equation describes a surface. But GeoGebra can handle this. So as you can see, sometimes it's difficult for computers to draw some implicit surfaces. So how can we do this? How can we tell or teach the computer to draw implicit surfaces? Is there any way or any method that we can develop? Well, that's exactly what we're going to be doing in this lesson. Okay. Okay, so first of all, we have to understand the problem. So let's do it. We have to understand what an implicit surface is, right? So let's bear with me, and let's say we have this equation, x squared equals 1. It's a very simple equation, okay? And this equation has two solutions, x1 equal 1 and x2 equal minus 2. And we can plot those solutions in the number line, right here. Here I have minus 1 and 1. So now let's move to 2 dimensions. I have my xy plane, and let's say I have this equation, x squared plus y squared equal 1. I know many of us, you know how to draw this, but for a moment, forget this, or imagine that you don't know how to draw this, okay? You don't know how to draw this equation. So I'm going to teach you how can we deal with this. So something that we can do is the following. We can treat y as a single variable or as a constant, and then we can simply isolate x squared. And if I isolate x squared, I can solve for x, because this is a simple quadratic equation as the previous one. So I get for 0, I get two solutions, x1 equal 1 and x2 equal minus 1, the same that we had before. And if I do this for many values of y0 that I treating this as a constant, what I get is many different points, okay? And these points, if I join them smoothly, I get my circle, as many of us was expecting. Now let's move to 3 dimensions. And just as a quick reminder, or as an advice, just as a warning, this video is not intended to okay, before continuing with the video, I just want to mention that this lesson, the only prerequisite I'm assuming is that you know single variable calculus, okay? That's the only previous knowledge you may have. But all the other stuff I'm going to explain to you step by step. So here we have a 3-dimensional space, x, y, and z, okay? So a common 3-dimensional space. And let's say we have this equation, x squared plus y squared plus z squared equal 1. So what can we do now? We can do the same. We can use the same strategy we used before. I can treat z as a constant, z0, and then I can isolate x and y. And we previously have solved this equation, right? X squared plus y squared equal a constant. So, for example, if z equals 0, we get a circle. And we can do the same for other values of z0. And by doing that, we get many different circles at different altitudes or different heights, because those are different z's, okay? Different values of zeta. And if I join all these curves smoothly, what do I get? I get my sphere, as we saw previously. Now, this is now coming back to our example of the line. I can call these points implicit points. Why? Because they are not explicit, right? I don't have an expression at the beginning. I didn't have an expression like x equal 2 or x equal minus 4. I had to solve the equation to find those points. So I can call those implicit points. In the second example, we had to solve another equation to find a curve. We had an explicit curve, so I can call this an implicit curve, right? And finally, on our third example, I had to solve certain equation to find a surface. The surface was not explicit, so I can call it an implicit surface, okay? An explicit surface, it would be simply a formula that tell me how to draw a surface, but this was not the case. So let's say that we had this equation x squared plus y squared plus z squared equal 1, and I can write this symbolically like this one, right? I have an expression of x, y, and zeta, and this is equal to a constant. Symbolically, we can have just that. But also, I can change x, y, and z for x1, x2, and x3. They are a triplet, so it's the same. And we can extend this and include many other variables. I can have, for example, an equation of n different variables: x, y, z, t, and other letters. So we can visualize this, but this equation is called, the graph of this equation is what we call an hypersurface, okay? Because it's like a surface but in higher dimensions. So let's continue. Okay, now I'm going to explain you how does a computer draw 3D functions, because we need first to understand how a computer draws a function, and then to see why it's difficult for a computer to draw an implicit function, right? So here we have it. For a 2 dimensions, we have here a function and the 2D plane. So what the computer does, where the computer samples many different points in the x coordinate and simply evaluates what is the value of the function, or I mean what is the value of y, like this animation is showing right now. And for 3 dimensions, it's basically the same. I have my 3 axes, x, y, and z, and I can have a bunch of points, the sample points, and then I elevate each point by a certain altitude, and this is simply by computing the function. Then the computer just join all the points smoothly. So this is what I was telling you about. We had a point x and y, and the computer simply computes the value of f, x, and y, this function right here, and elevates the point by that altitude. And this is how a computer draws a 3D function. That's why for a computer it's very simple to draw single variable functions or multivariable functions like this one. And I also want to mention that these animations were not made by me, This is from another YouTuber, and I'm going to attach the link in the description. He made a video about double integrals, really good video. But the explanation is what matters right now. So let's move on. The question we may ask right now is the following: is it possible to translate an implicit function into a normal 3D function? Because just think it for a moment. If we were able to do this, the problem is solved, right? Because as we're seeing right now, for a computer, it's very easy to draw 3D functions. Simply, we take many different points and elevate by a certain altitude. So if we can do this, transform an implicit surface into a normal 3D function, the problem is solved. So let's explore if this is possible. For that, I have this here. Let's start with the 2D case, okay? Because it's simpler. I have this equation, x squared plus y squared equal 1. So now we're going to draw the same curve, but in a different way. I can isolate y squared equal 1 minus x squared, and now what I can do is treating this as an equation. And if I treat this as an equation for y, I find y1 equal to square root of 1 minus x squared, and y2 the negative of the previous one. But remember, x can take many different values, okay? So these two answers, or these two solutions to our equation, are actually two different functions, so I can call them f1 of x and f2 of x. And if I draw them our xy plane, because we know how to draw single variable functions, it's easy, I get this and this other one. Oh, here this is one f1 and this other is f2, okay? And what are we seeing right now? We're seeing that if we take the union of these two sets of points, of these two curves, the resultant figure is our circle, right? So symbolically, we have that if I call A the set of the points of the circle, I mean the set of x squared plus y squared equal 1, this is equal to the graph, the union of the graphs of f1 and f2. So for a circle, our problem is solved, right? I can split a circle that was an implicit curve into two different functions. Then I plot those functions, and taking the union of its graphs, I get the circle, the full circle. So the problem is solved for this. So let's analyze if we can do the same for the 3D case. Let's move up to 3 dimensions, and I have right now the equation of our sphere, right? And let's do the same trick. I isolate z, and then I can solve for z, and now I have these two solutions. These two solutions, as you can see, can take many different values for y and x. So I can treat both of them as function of x and y. This means two variable functions, and we've seen previously how to plot this, right? So I'm going to plot for you these two variable functions, but it's not very difficult. You can learn. It's simply, there are some tricks. It's not very difficult, but for now, just let me draw them for you. Here I have the f2, and here I have f1. So again, it seems that the union of the two graphs gives us our initial sphere, right? So symbolically, this set A, that is the set of the points of the sphere, is equal to the union of the graph of f1 and f2. So for our sphere, the problem is also solved. We were able to translate this implicit equation into two different functions, and then we plot those functions and simply take the union. So it seems that it's always possible, but we can do ensure this just by two examples. So we can conjecture something. The question is it always possible to find those f, lowercase f, the function of x and y for a given surface? And this is an arbitrary surface, okay? An arbitrary surface described by an arbitrary equation, e of x, y, z equals 0, such that s, where s is the surface described by this equation, is equal to the finite union of those fi's. This is the question, right? We are wondering if it's always possible to chop or to translate, in some sense, our surface into smaller functions of x and y, which for a computer are very simple to draw. So let's analyze this. Let's explore this idea. So now we're going to play to explore the problem, okay? Here I have my 2D plane again. So what happens if I zoom? Let's see again. What happens if I zoom at this point right here? If I zoom in up, what I'm seeing right now looks like a function of x, right? I've made a zoom into my curve. Now let's see for the 3D case. I have my sphere, and what happened when I zoom? When I zoom in enough, our sphere looks just like a function of two variables, a function of x and y. So with this, however, there are some tricky points we're going to see right now. For example, what happens with this point? 1, 0. At this point, if we zoom, it seems that it doesn't matter how much we zoom in, it never resembles a function, right? And this is obviously not a function, because if I trace a vertical line, it crosses the curve in two different points, not in one. So this can be a function. And let's see now for the 3D case. For our sphere, if I look at this point, that I'm going to, okay. If I look at this point, let's see what happened. It seems that again, it doesn't matter how much I zoom in into that point, the surface never resembles a function of the variables, right? Because just look at this, it doesn't seem like a function of x and y, because furthermore, if I now trace a vertical line, it again crosses 2 times this surface. So this definitely can be a function of x and y. This is a function of x and y. So what are those points so weird? What's happening here? Pause and ponder if you can figure out what's wrong with this. Okay, so we're going to answer that right now. For this, we have to recall something called implicit differentiation, and I'm going to attach another video of 111 Bram if you want to remember this. But here's the very fast summary. I have my 2D plane, and I have my circle with the equation x squared plus y squared equals 1. And if we can make a trick, and we can differentiate both terms, x squared with respect to x and y squared with respect to y, and I have this. And this is not very accurate. I just have to add the x and the y, and then if I do this, that seems like magic. We can then separate, and we can treat the dx and dy like fractions, and I get this dx with respect to dy, or in other words the derivative, is equal to minus x over y. And remember, this dx dy is the slope of our tangent line, right, to the curve. So what's wrong with the point 1, 0? Why does this? Oh, first of all, why does this work? Well, here's the explanation. I can treat this expression as a function of x and y, and I'm going to call this capital F. Okay, this is a capital F of x and y. But from this and up to the end of the video, for shorthand, I'm just going to say big F. Okay, big F equal capital F. So I have big F, and remember we had something called differentials. Okay, in single variable class, the differential of f or lowercase f was equal to f prime of x by dx. So in this case, big F has two variables, so it has two derivatives, right? Because two variables, the derivative with respect to x and the derivative with respect to y. So what do you expect to be the differential? Well, simply the differential is the sum of the two derivatives multiplied by the respective differentials. It's just like a natural extension of the differential for a single variable function. But in multivariable calculus, we don't use the symbols, we use other fancy symbols. They are curly D's, like these ones, and we call them partial derivatives. Right? This is called the partial derivative of f with respect to x, and the partial derivative of x with respect to y. This symbol is also called sometimes del f, del y. So this is the reasoning behind why this works. And again, I'm going to attach a video in the description so you can review this if you don't remember it very well. So we have this is dx, the partial derivative with respect to x, and this 2y is the partial derivative of f with respect to y. So if we couple these two partial derivatives, we can make a vector, and this vector is called the normal vector. Why is this called this way? Because as its name says, it's normal. Normal to what? Well, it's normal or perpendicular to the tangent line. Okay, so now we're ready to see what was wrong with our point 1, 0. At this point, the point 1, 0, let's say what happens with our normal vector. Here's our tangent line, and remember the partial derivative of f with respect to y was equal to 2y. So in this case, our normal vector takes the form 2 and 0. So what's happening here? The partial derivative with respect to y, which is this axis, is equal to 0, which means that our normal vector has a 0 y component, and that's just causing when we have this is causing the tangent line to be vertical, and that doesn't allow us to describe a function right here. Now let's see what happens with the 3D case. In the three-dimensional case, we have this. We have a surface, and in our surface we can have a point, and at this point we can trace a tangent plane. Okay, not a tangent line, but a tangent plane in this case, because it's three-dimensional, right? The three-dimensional version of a line is a plane, and to this plane we can describe also a tangent vector per normal vector, and this is the normal vector to the tangent plane. And this vector can be described this way. If I have big F of x, y, z equals 0, simply the normal vector can be expressed as the partial derivative of f with respect to x, then with respect to y, and then with respect to z. Okay, it don't be scared with that. Just follow the explanation. The important thing here is the interpretation of the normal vector. So let's continue with our sphere. What was wrong with this point in our sphere? Well, at this point, the tangent plane look like this one. It looks parallel to the zeta axis, right? It looks like a vertical plane, similar to the vertical line in the 2D case. So what's wrong? Let's make the computation. Here, this is our normal vector, and here I have our equation. And now again, if I treat this as big F of x, y, and z, and I calculate the normal vector, that is this way, and at this point, at the point right here, this normal vector is equal to square root of 2, square root of 2, and 0. So what's happening? This third component, the k component, the component in the direction of the z-axis, that is equal to del big F del z, is equal to 2 zeta. And this one is equal to 0, which means that our normal vector has a 0 third component, or a 0 k component. That's why the tangent plane is indeed parallel to this axis, similar to the 2D case. And that's the answer. When we have this, it seems that it's difficult. When we have this, that the partial derivative of f with respect to z is equal to 0, it's like a kind of alarm, of a warning that is telling us, hey, you can't define a function here. It's not possible, okay? Here's a very tricky point. So let's move on. But I want you to notice here that this indeed is not the only point. Indeed, there are many other points. Infinitely many other points where this is not possible. And those points are located in this red line. These are the points with the normal vector when all of them has a 0 k component. So in all this red line, we can define a function of x of y. So with these observations, it's reasonable that we may find, or we may conjecture this. This is our conjecture. We think, or we are seeing right now, that for any arbitrary surface, or here it must say z, sorry, f of x, y, and z equals 0, if the partial derivative of x with f with respect to z is different to 0, which means that the tangent plane is not parallel to the zeta axis, then it's always possible to find a small region, okay? It would means make a big zoom into our surface, where the surface behaves like a function. This is our conjecture, and this is simply a summary of our previous observations. But the question is, how do we prove this? We can't simply let it as a conjecture, right? We want to prove this. So let's do it. But before going into the proof, let me explain you a final thing that it's going to be very useful to the proof. And this is another way to think about these implicit things that I showed you at the beginning. The implicit points, curves, and surfaces. So we're going to see implicit things as level sets. Let's see what this is. If I have this equation, the equation at the beginning, we can do this, and then if I pass the one to the other side, to the left hand side, now I can see this as a capital F of x, right? A function of f. And why is this useful? You may think we haven't made anything, but indeed we do. Because with this right now, we can plot this function in the 2D plane, which is this. This is our function. So now our problem to find the roots of x, or to solve our problem to solve this equation, x squared equal y equal 1, transforms into another different and more geometric problem. This is to find the points where this function f of x is equal to 0. And these points are right here, right? Are the points where the function, or the graph of the function, crosses the x-axis. These points are called the roots of f. Now let's move to 3 dimensions. So I have this equation, and I can do the same, and I call this big F of x and y. So this can be graphed or can plot as a 3D surface, right? I can graph this. This is the surface right here, and our problem to find the roots transform into to find those values, the values of the surface where it is equal to 0. In other words, the values of the surface where it crosses the xy plane. And these values contained into this circle, the red circle. Those are the roots of f of x and y. So let's continue. Now what happened with this function? This was the equation of our sphere, right? So if I do the same, this is a function of x, y, and z, big F of x, y, and z, but we can't simply graph this. Why? This function, what this function is doing is assigning a couple. This is a function from R3 to R. Why? Because it is assigning a triplet x, y, z to a single number. This is the value of the function at that point. So in order to graph this, we would need 4 dimensions. This is a 4 dimension, a graph in 4 dimensions. But we don't have 4 dimensions. We're simple 3-dimensional human beings, sadly. So what can we do? We simply give up? No, of course not. We mathematicians don't simply give up. So what we can do is the following. We can do a little trick, and I can tell this result of f, x, and y, I can call simple t, and t for time, okay? So with this, I can treat t as a slider, a variable. So what I can do this is see what is the shape of this equation if I vary t. So let's see it. As you can see, here we are varying the value of t from -1 to 0. And what we're seeing here is a sphere that is increasing, right? And this increasing sphere is indeed our graph, or the projection of our graph. And from all of these surfaces, the surface with this t equals 0, this is x squared plus y squared plus z squared minus 1 is equal to 0. This surface in particular is our root. Okay, this whole surface is the set of all the points where this function simple annuls, gets 0. This is our root surface in some sense. So you may think this right now, hey, we haven't made anything here, but trust me, indeed we actually did it. Just follow me. So it's gonna be useful. So let's see this. We can, as the previous one with hypersurfaces, we can now have this equation, and this equation, this is simply the same that we've seen so far, but with more variables. So when we have a function of many variables and we equal that function to a constant, the graph of this is what is called a level set. So for 2 dimensions, for one variable, we have what is called we have right here, and we can have many other lines. And if you project these points, we have this. Now for 2 dimensions, I have these surfaces, but this is simply the plane z equals 0, but I can cut with other planes. And again, I can project this to the 2D plane, and I get this. And for 3 dimensions, I have this right here that we need to animate in order to see our 4-dimensional surface. But again, this is simply our different level sets, and in particular the red one was our root, okay, our root set or zero set. And this right here, all these spheres is our projection, is like the circles right here. So this one are called level curves, and this other one are called level surfaces. And I like to call the first one the level points, although this name is not very usual in the books. So what we are seeing right now, we've seen that in this case we can treat indeed our implicit surface is simply a level set. What level set? Is the zero level set, because if I change this c by 0, I have f of x1, x2, blah 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 blah, xn equal to 0, and this is an implicit surface or implicit hypersurface. So we are seeing that implicit surfaces are just a single case of what is called level sets. Okay, so with this in mind, we're now prepared to the proof. So let's see the proof. Okay, the proof is as follows. First of all, in order to prove something, we have to formalize our ideas. How do we do this? Let's make a fast recap first. What have we learned so far? First of all, we've learned that implicit surfaces and what are implicit surfaces and what are implicit functions. Secondly, we have seen that implicit surfaces locally behave like functions, always whenever the partial derivative of big F with respect to z is different from 0. Okay, and with this term locally, I simply mean that when we zoom in enough, it behaves like function. Locally seems like zoom. And finally, we learned how to interpret implicit surfaces as the zero level set of a function of 3 variables, like this one. So with these ingredients, we can now formulate our theorem or our conjecture, but with more formality. This is what we want to prove. For a given function from R3 to R, this is a function of 3 variables, and a point x0, this is a point that we are finding. Let's say that this point is this point is equal to 0 when we evaluate the function of this point. This simply means that this is a point that belongs to the implicit surface, right? Because remember, the equation of our surface is f of x, y, and z equal to 0. And here I'm using this bold case to mean this. Now, with this condition, if the partial derivative of f with respect to z is different to 0, we've seen, or we've conjectured, that there exists a certain small region around that point. But in mathematics, we call this certain small region, we call these small regions neighborhoods, and that also writing with this curly n, and this is a neighborhood of x0 because the region is around that point. So there exists a neighborhood n of x0 where there exists a function f from R2 to R, this is a 2 variable function, such that big F of x, y, and f of x, y equal to 0 for all x, this means all the points in the neighborhood of x0. So if we follow with me, if we have gone with me so far, this should be perfectly comprehensible. But maybe, and just maybe, the last part is a little confusing. So let's explain a little bit this last part. You may be wondering why big F of x, y, and f of x0 equals 0. We haven't seen this before, what this part means. So let me explain you. Again, we have here our sphere. This is her equation, and let's say we found some surface. We found some function of f on x and y that is this pink region. But remember, this function is set equal to f and xy, right? This is how we write 3D functions. So the points on this pink patch take this shape, x, y, and z, but z is equal to f and xy. So this is the form that these points take. But the points of the pink sphere are also points of our implicit surface, which is the sphere, right? So this must also satisfy this equation, which means that x squared plus y squared plus f squared of x minus 1 minus 1 must equal 0. They satisfy this equation. Now, what if we have another different implicit function? The same holds. If I have, for example, this arbitrary implicit function or implicit surface defined by big F of x, y, and z equals 0, and I have this function of x and y, this pink patch, it has the same coordinates. This is the form that these points take. So these points, since also belong to the surface, must satisfy this equation, right? So they satisfy the equation, so we can write that big F of x, y and f of xy is equal to 0. And that is the condition that we've just written before. So I hope that this may clarify the term. So let's continue. Okay, now let's begin with the proof, once we've formalized our conjecture. The proof is the following. Let's say we have this arbitrary implicit surface defined as the 0 level set of this 3D function. And from now I'm going to simply draw as this mesh, this ghost version of the surface, because remember, why are we doing all of this stuff? Because we don't know how to draw our implicit surfaces. So this ghost version of our surface is representing that we don't know how this function looks like, and we don't know where the points of the surface actually are. But just to keep the track of the points, I'm going to draw it this way. So let's continue. Here I have my surface, and here's how it looks in 3D, because yeah, it's a three-dimensional surface. And now let's see it. Let's say that in this surface we find some point. We luckily have found some point, okay, the point x0. And at this point, also say, let's suppose that at this point the partial derivative of big F with respect to zeta is different from 0. And in particular, let's assume that it's greater than 0, which means that it's a positive value. So what does this mean? Well, as the picture depicts, this means that our tangent, if I have a tangent plane to the surface, our normal vector to the surface, whatever the surface is, whatever shapes takes, our normal vector should point upwards, okay? Because remember, this term right here is the k component of our normal vector, so our normal vector should point upwards. And if I know that this may seem that we are supposing too many things, but actually not, because it's not too difficult to find a point. And if we can guarantee that this is different from 0, the only possibilities as this is greater than 0 or less than 0. But the other case is very similar to this. So let's move on. Now if you close up to this region, we can draw a small circle And you can see, or you can guess, that at this circle or this sphere, you can see that it seems that all the points at this sphere have a positive seed component, right? It's like all of these points have also a normal vector pointing upwards. But again, the question is, how can we prove, how can we ensure that indeed we can find that sphere? How do we ensure that we can find a region where it's possible to find those pointing upward vectors? Well, in order to do this, we have to examine this function. So remember, this partial derivative of f with respect to x is what? Is also another function of three variables. Let's see why. For example, if we have our function big F of xyz is equal to yz plus xz plus yz squared, if I derive this with respect to z, what I get is the following: x plus 2xy. And as you can see, this is a function of x, y, and z. So indeed, our partial derivative of f with respect to z is another function of the same variables. So I can call them simply g of x, okay? I'm just giving it a name. G of x, it will be equal to the partial derivative of f with respect to z. So now let's explore what properties have this g of x. And in order to do this, we're going to see again our simpler case, the 2D case. Here I have our plane, and let's say this is our function. This is an arbitrary function of one variable, g of x, and let's say that we have found some point where it has a positive output, right? G of x0 is a positive. So, as you can see in the picture, with this condition it's possible to find a region around x0 such that the image or the values of the function are also positive, and this is shown by this circle right here. And we can also do the same for the 3D case. It doesn't matter, we have to notice that it doesn't matter how small our region is, it's always possible to find that region, okay? That region of positive values for our function. So, but this is also true if our function is continuous. Because let's explore this our function. Here again, obviously I can a positive point value, but it seems that it doesn't matter how I can take my interval around that point. It never contains just positive values, right? Because it always contains negative values, the region right here. And this is because our function is discontinuous. So, coming back to a 3D case, if we can ensure that our function g of x is continuous, and remember, all the normal functions, or at least the functions we are interested in, are smooth functions, smooth continuous functions. So we can guarantee, or we can ensure, that g of x is continuous. And if we in addition found some point where g of x is 0, and we have this point right here, because remember this is the partial derivative, so what do we get? Well, the consequence is that there exists a certain neighborhood, this is the analog to the interval in the 2D case, where all the points where the function also is positive. And what is the function? The function was simply the partial derivative, right? Remember that you would just simply change the name of this partial derivative. So what we found? We found a region where all the points have a positive value of the partial derivative of respect to z. And here is how it looked like. Here I have the zoom. Now I can zoom into this part, and I can trace my neighborhood, and inside that neighborhood I have that all the normal vectors will point upwards, as the picture depicts. This is because all of these have a positive value of this partial derivative. Now we found this, we can continue. So I'm going to draw the xy plane right here, and let's say that we have here our point x0 and y0. So this point will cross our initial point, right? x0, y0 and z0. So in this line I want you to notice that inside this pink line, the partial derivative of f with respect to z, this del f del z, will also be positive, right? Why? Because this pink line is inside the yellow sphere. So that this means, remember what this means. This means if this partial derivative is positive, this means that f is a strictly increasing function, which means that we can find a positive value. We can find a value of fz0 plus c where the function is positive, and we can also find another point, an equidistant point, where the value of the function is negative. So we find those 2 points equidistant each other, where here the function is positive and here the value of the function is negative. And if this doesn't feel very well, if it feel confusing, I'm going to explain it with the 2D case. Here I have our xy plane and I have a function. And this function, let's suppose that it has a positive derivative of our single variable function. And remember, what does it mean of a single variable function to have a positive derivative? It means that the function is strictly increasing, like this function right here. And let's suppose that we have a point where the function is 0, like right here. So with these conditions, and if our function is continuous, it's positive for us if I go a step in the x coordinate. If I simply take a step back, I can find a negative value. And if I can step forward and step c, I can find a positive value of this function. And this is exactly what we've seen so far. I can take a positive step. Remember, in this line, the points of this line has this form, x0, y0 and z. And since x0 and y0 are constants, this is simply a function of one variable, right? In the variable of z. So again, we can displace one step upwards, and remember, at this point, the value of the function is 0 because our surface has the equation f of x, y and z equals 0. So if I displace upwards at this point, because the function is increasing, it has to be positive. And if I go backwards at these other points, the value of the function should be negative. So I'm going to simply color code by red for positive and blue for negative. And now we're going to continue. So I want you to notice in the 2D case that we now just have these two positive and negative points. But furthermore, we can also find a whole region where all the points are positive and a whole region where all the points are negative, right? Again, this is because of the continuity of our function. So coming back to the 3D case, here we have it. Our 3D function sends the points in the 3D space that are depicted back to this sphere to points in the number line that is R. This is our function big F. This is what it does. So we had a point where the function is 0 and 2 points, one where it's positive and the other one where it's negative. So again, taking the same behavior of the 2D case, we can trace two different spheres where all the spheres, let's see what this property has. The point right here sends to the 0, this is the value of 0, and the spheres that is upwards maps to positive values in the number line, and the spheres that is backwards or downstairs maps to negative values. And this is because inside this yellow sphere, remember that our function has a positive derivative with respect to z. This is why this works. So, of all these spheres, we can choose simply a part of these spheres. So I can simply take the middle circles, and I have this. And now I'm going to plot this in the 3 dimensions, coming back to our original surface, and we have something like this. And as you can notice, the different disks can have different sizes. But what we're going to take now, we are simply going to take the smaller one, and the smaller one. Why? Because the smaller one would be the intersection of the 2 disks. So we have to take this one, the size of the smaller one, and I'm going to explain why just right now. I have this, and so let's now choose another different point, a point x star y star, and again if I trace a vertical line, this will intersect of our 2 disks into different points. And this is why it was important to choose the smaller disk, because if we choose the bigger disk, we couldn't guarantee that the intersection would be to the 2 disks and just once. This is why it was important to choose the smaller disks, okay, to have the intersection. So here we have the intersection in 2 points, a positive point and a negative point. So let's see what this means. At this line have the shape x star, y star, and z. So again, this is a function of z, and I'm going to call it big F hat, okay, another function. And this function is just a function of z, of one variable. So I can plot this in 2 dimensions, f hat versus z, and in this we have the following. I have a positive point and I have a negative point. But remember, our function f is continuous. So since our function f is continuous, f hat is always continuous, so it must hit 0 at least once. And this is obvious, right? Because you have to join continuously these 2 points, so you have to cross this it. This is also called sometimes the Bolzano's theorem. So one possible shape of our function is this, and this is another possible function, but we know that our function will cross the z-axis, but we don't know how many times will it cross. It could more than once. And here is the final step. We have to remember that these 2 disks and this point are inside our bigger sphere, right? Our yellow sphere. And what holds in this sphere? Inside these spheres, we have that the partial derivative of big F with respect to z is positive, which means that our function f is increasing. So, because of the monotony of f hat, it has to be increasingly. So it can't just hit once, because if in this case, for example, we can have a monotonous function. So because of the monotony, it will hit just once. And here we have it. So what we have here? Now with this we can guarantee that at this point our function fz has a unique point for f0, a unique 0, just like in the 2D case, okay? And this unique 0 is contained in the interval z0 minus c, that is this disk, and z0 plus c, that is this disk. And remember that this is contained. Okay. So now is maybe time to ask the following: when is all of this possible? All the things we've done for where is this possible? Well, remember, first we analyzed our bigger spheres, that is our neighborhood in yellow color, And then we simply try to analyze a smaller neighborhood. That is why I'm coloring this with pink. So all of this is possible inside that smaller neighborhood. So all of this is possible in the pink neighborhood of x0, in this cylinder right here. So in this cylinder, what we made? We've associated of our point x star, y star with a unique point in z star, right? So we've boiled a function of f from R2 to R. And now let's analyze what properties have this function. And this is of course valid in just for all x star and y star in the projection. What is the projection? This right here is the projection of the cylinder into the 2D plane. So what properties have this function? Well, let's analyze it. If I make this one big F of xy and fx of y, this is equal to big F of x star, y star, and f of x star and y star, just because this is the domain of our function. But what is the value of f of x star and y star? This is simply set, right? So this becomes f of x star, y star, and z star. But remember, what is z star? By definition, this is the point, a point where this value, the final value of this f hat is 0, but f hat is this one, so this is 0, which means that this triplet x star, y star, and z star is a point of the surface. So we've just found this function of xy is just the function that we were looking for. This is our implicit function. So with this, if we repeat this process in all the points in the neighborhood, we get this surface. And we are done. We've solved our problem. Now we know how to transform our implicit surfaces into an implicit function, and we know that when is possible. So it may see, right now you may say, well, this is fake. You haven't gave me an explicit formula for this implicit f. But just reflect. We've just made something really awesome. We began with an arbitrary surface that we didn't know what its shape was, and we began with just one point that had a positive or a non-negative derivative with respect to z. And with this simply very scarce conditions, we were able to find a function that maps part of the surface. And now, just let's think, if we can repeat this process for different points in the surface, we can build our complete surface, right? Just by joining together those different patches of functions. So we've solved our problem. This is simply amazing, because this is an completely arbitrary surface. And just if this wouldn't be enough for our theorem gives us even more. So this is, if you're not satisfied with this, there is even more. Here it is. The implicit function theorem also helps us to approximate the surface. Here's how. We're going to see very fast again our 2D case. Here's our implicit curve, and here let's say we have a patch of our function and a point. At this point we have a tangent line, and perpendicular to the tangent line we have our normal vector that has these components. So now let's move on, and let's see in what other way we can compute the slope of our function. Well, very easy. If I have this single variable function, I can simply take the normal derivative, and this gives us the slope of the tangent line. So with this information, I can build a new vector. This vector has 1 in the y-axis and f prime in the y-axis, and if I sum them two vectors, I can build a new vector that just simply fits in the tangent line, and I can simply call t for tangent. And you can corroborate that the slope of this vector is equal to the slope of the tangent line, is f prime. So whatever, let's see what happens when I take the dot product of these two vectors. This is equal to simply this, and if I operate this, I have this expression of partial derivatives. But remember, what property has n and t? This is the normal vector to the tangent line, so this is also normal to this tangent vector, which means that they are perpendicular. In other words, this dot product must be 0. So if this is 0, I can now isolate the derivative of x. So I find that f prime of x equal to the negative of the partial derivative of big F with respect to x divided by the partial derivative of big F with respect to y. And if you want a mnemonic trick, here it is. I can also write this derivative in this way, and since our equation is actually y equals f of x, I can write in this other way. And remember, I can plot this in the expanded form as we see, and if you can see in this formula, it seems like we've just simply inverted the x and the y and put a negative sign. And indeed, if you can treat this as fractions, it's like you can add simply the sandwich formula for a fraction, but with a negative sign. So with this in mind, I think that it's due time to pause and ponder and try to think in the following. What would you think that it would be the shape if I have this implicit surface? What would be the shape of this partial derivative with respect to x and this other partial derivative with respect to y? Okay, so now let's go with the answer. Here I have a 2D surface, a 3D surface. So in this 3D surface, let's simply draw a point, and to this point let's make a cut. This is a cut when we're going to cut with a plane that is parallel to the y-axis, and the intersection is simply a line, and I can erase the other part of the surface to what this line. And at this line I can trace a tangent line, right? So with this I can also plot my normal vector. So I'm going to zoom them up, and I have this, and let's simply do the same. The key here is to notice that the slope of this new line is equal to this partial derivative. Let's see why. Remember what means to take the partial derivative of f with respect to y. What this means is the following. This says choose a constant y and then derive the usual derivative with respect to y. And what are we doing here? We're doing exactly that, because this plane represents a constant value of y. This is a plane that is y equal to some constant. Then we have this line, and to find this slope we are treating the derivative with respect to x. So that's why this slope is equal to this partial derivative. With this information we can arrange, or we can build another tangent vector similar to the previous case. I have this, and I just want to notice that this has this I hat and this one is the k hat. Okay, this is the unit vectors, and this is my tangent vector, and I can take again the dot product, which is equal to this product of partial derivative. By operating I get this, and again because t and n are normal vectors, this has to be 0. So rearranging the expression, I find that the partial derivative of f with respect to x is equal to the negative of the partial derivative of big F with respect to s, and divided by the partial derivative of big F with respect to z. And again, our mnemonic trick also works. So this is how it works now. You can simply pause and say that this is very similar to the previous expression. And if we repeat the process for the other variable, I get this one. This is the partial derivative with respect to x, and this other one is the partial derivative with respect to y. So now we know how to approximate, because remember, the partial derivatives tells part of the story of our three-dimensional function. With them, we are able to build our 3D plane, and that 3D plane is a linear approximation for our surface. And so do this. This is the implicit function theorem. Thanks for watching.